What I have for you today is a general overview of FRP, so a little bit of FRP 101 for those folks who are not that familiar with it. Some information on how we conduct the corrosion studies and some of the stuff that we do there in Dublin, Ohio at our laboratory. And then we'll talk about some of the big projects that have happened. Really, the idea here is to give you the scale of capability for FRP. A lot of engineers don't realize the scale of some of the equipment that's out there. And then also just kind of give you some information on what's going to be going on with lithium processing coming up in the near future, because it's kind of a hot topic for folks with lithium and its role in battery devices. So as mentioned, I manage the Corrosion Science Center, which is located in Dublin, Ohio, just outside of Columbus. And we focus on key markets: mineral processing, pollution control, so power, that type of stuff, chemical process, pollution control, different types of chemical manufacturing applications, pulp and paper, infrastructure. And our key product line is Derricane, epoxy vinyl ester resins that go into the corrosion applications. And our Derricane corrosion guide really is kind of the hallmark of the industry for guidance into using FRP in a number of different corrosion applications. My team is made up of Michael Stevens. Probably a lot of folks in this room are familiar with Mike. He's been around for about 45 years, just a walking encyclopedia of FRP knowledge. So if you run across something obscure, feel free to reach out to us. Chances are Mike has probably seen it at least a couple times, if not 4 times. Lisa Atkins is also one of our technical service representatives. She's got about almost 30 years behind her. She just does a great job. She does a lot of the management of our resin recommendations that go out into the industry. Benito Rodriguez is on the West Coast. He manages the corrosion and fire retardant product lines there. Steve Fingerlow is a tech service rep out of Columbus, Ohio. So he manages a lot of the activities around that area, and then also manages a lot of the work that goes in and out of our laboratories. A lot of the product development and tech service laboratory work that we do. And then I'm the manager. So my background is in polymer chemistry. I've been with INEOS going on 21 years now, I think so. Well, Ashland originally, and then INEOS. You will have seen too, there was the Hetron product line that Ashland used to have. And by and large, it's important to note that the important resins from the Hetron product line, the Hetron 980, the 980-35, those resins all were rolled into the Derricane product line because they were unique. Hetron 922, very close to 411. So Hetron 922 has pretty much been obsoleted. So that's just some of the background of what we do and the products that we work with. And so as mentioned, I'm going to go into a little bit of FRP 101. I'm going to talk about the hydromet process because it really is an interesting process in that it lends itself perfectly to fiber reinforced polymers. The types of chemical environments, acid chlorides, oxidative environments that alloys struggle with are really ideal for FRP. How we know which materials work, how we conduct corrosion testing. A great aspect of FRP is its ability for easy remote fabrication, quote unquote easy, but remote fabrication of very large vessels. How we deal with coatings and linings, abrasion resistance, just a few of the case histories that I mentioned to give you an idea of the scale of the equipment that's out there in the world. And then talk about lithium. So where FRP kind of falls in, as you look at this a scorecard, the infrastructure scorecard that came out of the recent Infrastructure Investment Act. And by and large, composites have a role throughout all of these applications. Water treatment, energy, hazardous waste management, pollution control, and then as mentioned, upcoming roles in power production and lithium harvesting. But overall, we didn't really score too well. But composites really have a role here to help make things better. You're going to see a lot of composites going into infrastructure applications, and then, of course, as you all know, a lot of corrosion applications. So as we look at the hydromet process, by and large, what it is, it's an aqueous chemical processing environment. You start out with crushed ore, so like all the mining that happens where the ore is brought up out of the ground, it's typically piled into a leach pile. Essentially what that is, it's a mound of rock on top of some type of membrane, and then they trickle acid down through that. It'd be hydrochloric typically. And there's typically an acid plant that's right on site that produces that acid. And so the heap leach has the minerals that you're after extracted out of it, and then that goes into a clarification process. So you're going to see some rather large countercurrent decanters, that type of stuff, in the next couple of slides. But you see that there's a number of different tanks, purification precipitators, pollution control. In the case of something like copper, typically there's an electrowinning process. So those electrowinning cells are typically made out of a polymer concrete. So a number of different roles for corrosion-resistant resins across the entire production process, not to mention just all the miles of pipe that are associated with this. And again, these are all acid chloride type environments in the case of heap leaches with hydrochloric acid. And then there's a number of different washing steps that could have caustic chemical environments too, where FRP also does a really good job. So when we talk about the challenge of corrosion, as you look at it, really everything would be carbon steel, if it could be, because it's inexpensive, great strength, easy to process, easy to recycle, all of these different things. But it doesn't do all the things that we need it to do. So that's over the decades, alloys have been developed. And by and large, the metals, how they work is you have your metal substrate and they develop an oxidated layer. And that layer is called the passive layer. And that essentially, that oxidative layer forms and protects the underlying metal substrate from further corrosion. But over time, what you have is you have a loss of that oxidative layer, and then it regains, it's lost, and this is known as the loss rate. And so engineers are typically very familiar with loss rates, but they're not familiar with fiber-reinforced polymers, because fiber-reinforced polymers, really, you only have a brief chapter of this, I think, in a number of different education series. Even me as a polymer chemist, we touched on FRP, I think, for just like a month, and even that. And so what we have with polymers is they either work or they don't. And so they're either compatible with your chemical environment, or they're going to be degraded relatively quickly. And so a lot of what we do at the Corrosion Science Center is really understand what this phenomena is. And so as you look at the polymer network, you can have a little bit of permeation that occurs, and how we govern that and how we design those corrosion barriers, by and large, what we do. We really are not involved at all in the underlying structural layers. That's more for the engineering teams to focus on. It's a little bit outside of our wheelhouse. We're just a bunch of chemists. But at the end of the day, what we're trying to do is identify the right materials to be used in the right application. We're not trying to displace alloys or metals where they make sense. We want to make sure that FRP is used where it should be used, so that we don't have failures, so we don't get black eyes. That's really our goal here. So when we talk about fiber-reinforced polymers, really what we're talking about is resin and some type of reinforcement. Typically, it's glass reinforcement. I'll get into more details about the types of materials in the future slides. But what we look at is the thermoset resin. Typically for corrosion applications, it's an epoxy vinyl ester resin or Novolac epoxy vinyl ester resin. The Novolacs have higher resistance to acids and oxidative environments. They also have higher temperature performance, but they have a downside. They don't handle caustic environments as well as the regular bisphenol A Novolac epoxy vinyl ester resins. But it is the matrix that really determines the corrosion performance of the composite material. And then it's the reinforcement that we rely on for the strength and the reinforcement of the corrosion barrier, and then also the construction of the structural layers. So as we look at the different types of materials that are available, we essentially produce 3 families of thermoset epoxy vinyl ester resins. And essentially what they are typical epoxies. Like if you had an epoxy amine system, if you buy a glue at the hardware, you have one tube that's clear, that's typically your epoxy, and then you have another tube that's brown, that's your amine. Well, what we do is we don't have an amine cross-linking agent. What we utilize is methacrylic acid to build these polymers. So that means that we can use what's known as a free radical polymerization process, and it's a very flexible process. It's an easy chemical reaction to get very consistent mechanical properties. Ultimately, with a thermoset resin like our epoxy vinyl ester resins, as long as you cure it, it doesn't matter how you got it cured, it could take 15 minutes, it could take an hour. But by and large, the rule of thumb is as long as you cure it, you're going to guarantee a minimum performance level from a corrosion performance standpoint and a mechanical property standpoint. So that's an important thing to realize. There's an entire science in understanding how we know how it cures and how we evaluate cure after a piece of equipment's been fabricated. I think some of that's going to be covered elsewhere throughout the series, but if you have any questions about that stuff, we're always happy to dive deeper into that type of conversation with folks. So first we build the resin, and then we identify the type of reinforcement that we're going to use immediately in the area of the corrosion barrier that's going to be interfacing with the chemical environment. And so what we have are these different types of veils. So carbon veils are quite often used if you need conductivity, because maybe you have like an electrostatic buildup concern or something like that. Also, the carbon might be used in a hot caustic or hot acid chemical environment. They typically perform very well in those applications. For other lower temperature caustic type applications, you'll typically see a polyester veil. Typically Nexus is what you're seeing out there. And that polyester veil is very good because it's resistant to caustic attacks. It also performs well like in hydrofluoric acid type applications, all that kind of stuff. All that information is in our corrosion guide if you're interested about that stuff. But by and large, the big workhorse of the industry has been sea glass veil over the decades. And recently we've seen Owens Corning exited the North American sea glass veil market, so it was kind of interesting, and they just didn't, I don't really know what all the issues were there, but I think there was just a need for them to kind of phase out, and they began to focus more on they have ECR glass veils called the Advantix veils that they've been more focused on. And that was a hot topic last year. I think we're kind of over the hump of that big concern that a lot of folks had with that change out of the veil in the industry. But by and large, sea glass veil is the main workhorse. So when we talk about a corrosion barrier, typically what it is, it's the first 100 mils on top of the structural layer at minimum. It could be bigger than that. But what you have is you have your veil layer, and it's about 10 mils thick. And that layer is about 90% resin. So it really does all the job of protecting the underlying structures from the chemical environments. And then what you have next is chopped strand glass mat. And so what you want there is you want discontinuous fibers. You don't want corrosion to be able to attack a single strand of glass and travel throughout the composite, rapidly degrading the performance of the composite over time. And so the chopped strand glass mat combined with the veil really is what the corrosion barrier is. Some chemical environments, we might recommend that you use 2 veils. You double up this corrosion barrier, this type of stuff. All the special cases, if you're interested in that, we can talk about that outside of the presentation here today. So as you look at FRP and corrosion performance versus alloys, really what this slide is telling you, the take-home message is that acid chlorides, acids really are something that FRP made with epoxy vinyl ester resins handle quite well, much better than something like a 316 or an LiC276. And so at the end of the day, that's the reason why FRP materials really have become the material of choice for acid chloride type environments. Another area that you'll see is where rubber linings might be used in place of an FRP type material. And the challenge with rubber linings is they're great, they do a great job, but what you have often is a carbon steel vessel with a rubber lining on it. And that rubber lining is, only so thick. And if something were to happen to penetrate that lining, you now have chemical environment going across that rubber lining, and then you have the carbon steel substrate exposed to a chemical environment that it is not suited to deal with. And so what you see is rapid corrosion and degradation of the tank wall behind the rubber, and then you wind up having disbondment of the rubber and failure of the vessel. And so over the past a decade or so, we've seen a lot of folks that have gone in and replaced these rubber linings with FRP, because it's often a challenge to try to I guess, get the same type of shop application of a rubber lining in the field as you do in a shop controlled environment. So how do we know how this stuff is going to perform? We actually do empirical studies. We do corrosion resistance evaluations. So I don't know if you can see this quite well, but what this is this is a reactor in our lab, and these are ASTM C581 corrosion coupons. And there's a method for making these coupons. It's a standard that's been out there for a long time. And by and large, what they are meant to do is to simulate the corrosion barrier on the wall of the vessel, but from both sides. And so you can just totally submerge that coupon in the chemical environment and monitor its degradation or change over time. So change in appearance, change in barcode values, hardness values, change in modulus, flex retention, just is there wicking occurring? Can you see fiber prominence over time? All of these things are aspects to that test method. And so in this case here, we're looking at flex strength retention. This was for a pretty aggressive chemical environment, 60% sulfuric acid at 99, a little typo there, at 99C. And so that's pretty chemically aggressive. That's not something we recommend. This was a specialty corrosion study for somebody that had a specific chemical environment. So you're not going to see that in our guide. I just want to make sure you understand that. But you can see, so the epoxy vinyl ester resins, really good workhorse corrosion resistant resins. The Novolac epoxy vinyl ester resins have more resistance to temperature and to oxidative environments, and you can really see that shine in the data. So the first month they're doing okay. By the time we get to the third month, we start to see a big difference in the performance of the epoxy vinyl ester resin versus the Novolac. And you can see that the Novolac really just did okay in that application where we had to stop the Novolac. So this would be like a 411 versus a 470 here. And this little bit of a dip you see in the first month is something that's very common in these corrosion studies. Once the FRP equilibrates with the chemical environment, you'll kind of see that steady off. And by and large, what we're looking for is no more than about a 50, and then in some cases, depending on the study, a 70% drop in mechanical properties. That's the pass or fail mark that we're typically looking for. So this is a direct empirical study. And then other things that we do, so we might have run these studies back in the 60s and 70s, so we kind of know what's going to work. And then we wind up having a case history. And the case history is really what we want to have ultimately. That's really going to tell us what the performance is. Here's a great example, too, of something that's kind of unique. So this is a solvent extraction study that we did for the Goro Nickel project, starting way back in the early 2000s. And so in that extraction process, you have aqueous and you have solvent chemical environments combined in one application. And the goal there is to try to dissolve your metal salts in the water, and then use a chelating agent that can be extracted by the solvent to pull the metal out of the water into the solvent, purifying it from all the other materials that came along from the extraction process. And so what we have here, so we have the hydrochloric acid, and then we have the solvent layer, and then you have this interface. And so what we were looking at was trying to understand which material is going to perform the best. So what we looked at are Novolac epoxy vinyl ester resins versus regular epoxy vinyl ester resins. And we looked at to see if the brominated analog would do well. So instead of having, so the brominated analog is the same polymer. So 411 with bromines attached at strategic places on the polymer backbone is the Derricane 510 series of resins, the 510A, B, and C. And so that bromine, right where it is, sometimes prevents specific chemical attacks in these types of environments that give better performance. We have a whole paper on just talking about how a brominated resin performs better in hypo service versus a non-brominated and all that kind of stuff. But so we were trying to figure out which material was going to be the most suitable. And in this case, what we found was that in all the key factors, the Novolac-based materials, the brominated analog and the regular Novolac, perform much better for this solvent extraction application specifically. And so these are different attributes that we wanted to know that we use for our measurement of performance. You can see that the regular vinyl esters didn't do well, the Novolacs did much better. And then eventually, that's what led to the recommendation of the 470 family and these pulse extraction columns. I won't get into, there's a lot of ins and outs on this project because it was one of the largest scale ones. So I think probably there's 5 people in this audience that we could spend 2 hours talking about just this project. So a lot of horror stories, but a lot of victories too at the same time. And so, but chemical evaluation in our laboratories led to this real world example of brand new technology. So this is the first pulse columns that were ever out there. So this is to win mainly copper, but other metals as well. And so, and then on top of that, you see all types of other types of process vessels that are made out of FRP, just because of its suitability for the reagents that are used in these chemical extraction processes. So now let's switch gears a little bit and just talk about the versatility of fabricating with FRP. And so a lot of what folks do, so if you are having a piece of equipment constructed for you, you're going to typically hire an independent inspection firm, like the fine folks that have put on the show here. And those people are really going to be your eyes and your ears in the shop, because that's what they do every day. You know, if you're a plant engineer, you can't be expected to be an expert in fabrication of FRP. If you can, kudos to you. But the best thing is to really have somebody go in there and know what they're doing. Now, so a typical fabrication method for pipes and for vessels is filament winding. And what that is you have your glass reinforcement. So first you build your corrosion barrier, typically by hand, on the mandrel. And then you have your glass roving that goes through a resin bath and then wraps on the mandrel. And then there's a specific wind angles that are prescribed so that you have the right mechanical strength of your final product. And there's different, you can have this, in this case, this is a carousel or a horizontal wind versus a vertical wind versus what you have here, which is a horizontal wind. And so in this case here, this carousel winder is something that you can erect in the field. There are vessels that have been erected in the field that are over 120 feet. Walls that are 2.5 feet thick, just super, like the size of a cathedral. I mean, just absolutely amazing pieces of equipment fabricated in the field using this method. Here, what you have is a mobile shop that's been erected. Inside of there is the mandrel. And then what you have here, these are smokestack liners, affectionately called cans. And so these get put into the smokestacks on a coal-fired power plant. So you put it in the bottom, you jack it up, you bond them together, you jack it up, and that's how these chimneys are built inside of the concrete chimney that you can see next to the plant. And so just for the scale, that's a Ford F-150 pickup truck right there. That's a stack liner that was made inside of that remote fabrication shop. So just an idea of the power and the capability of this type of material. So as you look at mineral processing applications, a lot of these are in remote areas. So this is, I think, of interest to a lot of folks because you can build large equipment out there in the field. A twist on this is tank ablation. Tank ablation is where you build the walls of the tank in a shop environment, so you get really, pretty much better labor costs, good quality control. You build all the walls for the vessel in the shop. You put them on a flatbed, you ablate them, and you nest them inside of each other. They arrive at the place that you want to erect your tank. You allow them to relax back to their original shape, and then you bond them together, and then you have an almost shop quality vessel rapidly assembled in the field. So it's a little bit more cost effective because, as you imagine, sending all that remote labor, it's a lot of money. You got to ship all your materials to a place, but it's pretty cost competitive versus other techniques for building corrosion resistant equipment. Another great example, these are the extraction vessels at the El Baleo mineral processing facility in Baja, California, Mexico. These were all fabricated on site. And so all with abrasion resistant liners. So these are processing hydrochloric acid with rock slurry to try to win the metals. Just amazing. Other things, vinyl ester resins are used in a number of different lining applications. There's entire companies that produce linings and coatings based on our epoxy vinyl ester resins. This is an example of a sheet line vessel. So this is actually a free floating liner in a large countercurrent decanter. And in this case, what you have is the vessel itself is quite large. They shipped all the panels together, and then they assemble them at the site to have this large. And I think Jet's going to go into this type of technology in a little bit more depth in the next presentation. So abrasion resistance, that's often the challenge with FRP. If you have slurries, you have to worry about abrasion of the FRP. And how we can achieve good abrasion resistance is by adding hardeners such as silicon carbide. So we have a bunch of different abrasion papers that can help you understand, do you need an abrasion liner or not? Feel free to talk to us in more detail about that. And then also there's just a number of types of linings. We have a little primer on how to line a metal vessel. It's not meant to be, the only thing you need to do it, but it's a good primer to understand how you go about doing this stuff. So feel free to reach out to us for that information. So we've actually done a number of studies over the years to understand what concentrations of silicon carbide or say fine silica are going to give us the best performance. There's a little trick to fabricating with these materials, so there's some things to understand before you prescribe this, and you really want to understand. If you need an abrasion liner, go ahead, request it, but if you don't, you really shouldn't because it adds a little bit of a twist to the fabrication process. Here's the example of the Baleo project. Just look at the scale of this equipment. That's the loose liner and the CCD going in. Just amazing equipment. Over here you have the extraction tanks that we mentioned that were remotely fabricated, acid production plant over here. Also, all of this process was designed to operate on seawater. So if they had used metal to harvest the seawater for this process, they would have had ancillary corrosion issues with with that metal. So just everywhere you see here, this is a lot of FRP. Tons of mixer settlers. So we talked about that, separating the aqueous acid environment and then getting the metal with the chelating agent into the solvent. That's what these do. So this is a continuous process. So you have mixing, decanting, purification, mixing, decanting, purification, until you go through the recovery. So a number of different applications out there in the world these days that have used these with great success. Another case history is the Long Harbor project. So lots of FRP here, throughout here. These scallop covers on top of these clarifiers. The clarifier unit is just like a higher end purification that goes further down in the process after the countercurrent decanters. Electrowinning cells for winning of the copper. A number of different types of vessels, extraction units. Just some of the scale of some of the vessels that were shop made and shipped up there to Long Harbor. Pretty impressive. So the thing here for you engineers to realize, a lot of this has been done. So it's not a new thing. So you shouldn't be that worried at looking at if can FRP work for your application. So FRP and lithium. And this has really been the hot topic. Over the past, I want to say 5 years, number of different firms that are out there, they literally send us a spreadsheet of an entire plant. And they want us to go through that spreadsheet and make resin recommendations. And 5 years ago, we made a ton of these, and then all of a sudden now, with this environment changing, we're seeing all this kind of turn on. The Salton Sea application, geothermal power plants at the Salton Sea, for years and years, these things were operating, and nobody realized that they were throwing lithium-rich brine back down into the earth that went through this plant. So now they're bolting on lithium extraction plants to the side of these power plants. So winning lithium. So it said at the Salton Sea that there's enough lithium for us to really get our lithium requirements up and going. There's other folks that are looking at technologies using FRP to recycle lithium. So what they're trying to do is get this lithium cycle going so that you have winning of virgin and then recycling of used lithium to keep the process moving forward to meet our energy needs. So pretty exciting. And again, how do we know what's going to perform in the right place? We've done the corrosion studies already. So lithium carbonate, lithium chloride, lithium hydroxide, different types of chemical environments. This is more caustic. So by and large, we know for a number of these applications, if it's about 180 or less, typically Derricane 411 is going to be used. If it's over that, typically Derricane 470 is going to be used. But if you have a caustic environment, high temperature, you're going to want to look at Derricane 451, the old Hetron 980, because it just does a great job. Really, a really interesting resin there, which I won't get into a lot of detail. But what we're saying really is that coming up in all the areas of lithium winning and recycling, FRP is going to be the material of choice because it's able to deal with that chemical environment perfectly. Just a word on maintenance. We're going to see Tom get into some of this stuff. And so thermal imaging is something that a lot of folks use out there in the field. I can't recommend this enough. It's just a great tool to use. I'm not going to steal anybody's thunder by getting into it too deep, but it just makes sense. Get new equipment, take thermal images of it, especially pipes. Pipes where you have elbows, where you have process eddies that are going on. You can see right there's been thinning. So if you want to inspect your vessel, where should you inspect it? Well, you probably should start taking a look at that hotspot. Ultrasonic testing, not that hard to do. It's something that you can be trained on, or you can hire an expert in that area. But then there's other techniques, some X-ray. There's RFID, which I don't talk about here. That's something that's coming more online, where you look at degradation and you have like an RFID device, like what you use to scan your credit card. That if that degrades, that once you lose your signal, enough corrosion has happened that it's penetrated into the laminate, killed your FRD sender. And so now you know what the state of your corrosion barrier is. A number of exciting things that are out there. So ultimately, what I hope I did for you guys was give you a little bit of an overview, kicked off this exciting forum that we have here for the next couple of days. And I hope you found this information worthwhile. And if you have any questions, please feel free to reach out to us. My colleague Joy Bennett is also here. And then also there's other folks that know us quite well and can refer you on to us. So I hope you found this interesting. And thank you very much.